Okay, today we're going to do our fourth practice of related rates word problems. So here is a sphere, because this problem is going to be a volume of a sphere problem, right? Here's my haphazard sketch of a sphere with a radius r in blue. So the radius of this sphere is increasing at a rate of 4 millimeters per second. And we want to know how fast the volume is increasing when the diameter is 80 millimeters. So let's set up our problem, right? I've already written down the volume of a sphere formula because you probably don't know it off the top of your head. Most people don't. I don't. And what else do we know? Well, we know that the radius of the sphere is increasing at a rate of 4 millimeters per second, but what does that mean exactly? What that means is that the rate of change of r is 4 millimeters per second, and that means that the change in r over the change in time is 4 millimeters per second, and we know how to write that down. That's dr over dt. Well, not over. It's not a fraction, you guys. It's dr by dt. It's one thing. You can't separate it. Let me just make that clear. I always say over, and I know what I mean, but obviously other people don't know what I mean. And that is 4 millimeters per second. That's important. We're going to need that. So that doesn't look quite right, does it? Okay. So the first thing that we're going to do is we're going to differentiate our formula right here implicitly. So we're going to differentiate both sides. Now, the left side is just going to become what we're solving for, right? It's going to become the change in the volume of the sphere over the change in time. And then this side is going to be a little bit harder, but not really. It's just that you have to remember the constant multiple rule, which is that if you're taking the derivative of all of this and you have a constant, you can just pull that constant out. So what we're actually going to end up with is 4 over 3 pi times d by dt of r cubed. Okay, so the change in r cubed over the change in time. Well, hold on a minute though, because r and t are not the same variable. Variable mismatch means chain rule. So we're not going to go too much into detail about how to apply the chain rule. You probably know that by now if you're doing related rates. So what we're going to do is we're going to do 4 over 3 pi times, okay, r cubed, the change in r cubed over the change in r times the change in r over the change in time. So that's the outer function, which would be t cubed, right? And r cubed, and then the inner function, which is r. Well, okay, what we have here, sorry, did I get those variables correct? The outer function is r cubed. And the inner function is r. Seems like the outer function should be t cubed because we're differentiating with respect to t. Let me think for 1 second. The variable mismatch is t and r. So if we have r cubed, and that's a composite function, and we're differentiating with respect to t, then this is t cubed composed with r, which is r cubed. So when we're doing that, we're going to do 3t squared, except that we're going to substitute r. Right. Sorry, I was having a senior moment. So yes, the variables are correct. I was just not understanding why I was doing what I was doing, but now I understand. Troubleshooting, you guys, is important. And the reason I'm not going to redo this video is because it's good to think about these things and understand why we're doing what we're doing. So, and then it feels really good to get to the answer when you think about it, right? So you have 4 over 3 pi times 3r times, well, we know what this is. We know what the change in r over the change in time is. It's 4 millimeters per second. So 4 millimeters per second. Now, let's make sure we keep these brackets. I guess you probably wouldn't need them, but we want to keep the pi, so let's just keep them. So we're going to solve for this change in the volume of the sphere over the change in time when the diameter is 80, right? We're looking specifically at when the diameter is 80, which means that the radius is 40, which is important because that's what we're going to substitute. We're not actually working with diameters here. Well, this equals 4/3 pi times 340 millimeters. Let's write the millimeters. Otherwise, we're going to be like, what's the unit? Okay, so times 4 millimeters per second. We don't really want to get rid of that pi. That gets annoying. So these 3's are going to cancel out. And we're going to end up with 4/1 times pi. So let me write it. I want to put my equal sign right underneath it. But since I can't because of all of this mess, I'm going to just write it down here again. S by dt, and then I'm just going to write it down here again. R is 40 millimeters. Okay, equals 4 pi times 4 millimeters per second times 40 millimeters. And what's that going to equal? That's going to equal, so we're going to take this 4 times 4, okay, we're going to make that 16 pi times 40 squared. Actually, there's a square here. There needs to be a square there. Sorry for the confusion, but of course, when we differentiate this doesn't become 1, it becomes 2. So 2 troubleshootings in this particular video, but that's okay. So this is going to become 40 squared millimeters squared per second. And you could roll this out. You could multiply all this. Do you want to? I mean, it comes out to 80,424.772 if you round, right? I mean, I'll write it down because why not? 424.772. I mean, that's just not as nice as this right here. So we're gonna stick with this. I prefer this. It's the same thing. You can put it into your calculator if you like, but that is our solution. So if somebody asks you, or if you're doing this on an exam, you need to write a sentence answer because it's a word problem. You can say, the volume of the sphere is increasing at a rate of 16 pi 40 squared millimeters squared per second.